If you model collective behavior using classical dynamical systems, the mathematics will almost always force one of two outcomes. The population will either explode into unbounded divergence or fuse into a static equilibrium. Whether analyzing Hegselmann-Krauss opinion dynamics or a Langevin physical system, standard state space assumptions inevitably destroy structural pluralism. The math dictates that dissenting configurations must eventually be eliminated. The Recursion-Collapse-Recombination framework, or RCR, proves the existence of a third, structurally stable phase. Here, in the center section of this 1D phase space simulation, we see active metastability. A dense majority coexists with a distinct oscillating minority cluster that neither merges nor escapes. As the data overlays track the simulation, active metastability requires three strict mathematical conditions. First, persistent dispersion, meaning the median absolute deviation is bounded strictly above zero. Second, continuous activity, shown by the strictly positive trajectory variance. And third, global physical stability. The system is highly active but never diverges. To construct this state mathematically, we must build the exact operators that generate it, demonstrate why traditional static multi-well models fail to maintain it, and map the precise analytical boundaries where this dynamical phase can survive. Proving the existence of active metastability provides the mathematical vocabulary required to describe systems where descent and variation permanently endure. This is an n=2 canonical system, the minimal environment required to isolate the micromechanics of the RCR triad. We have one majority agent resting at 0.5 and one minority agent out at 2.0. The first operator is recursion, or F. This provides a self-reinforcing, nonlinear amplification of deviation. It pushes agents outward. Because it is self-referencing, the minority agent receives a larger recursion force than the majority. Next is the collapse operator, C. This acts as a dual-scale restoring force that pulls the agents inward, ensuring system dissipativity. The further an agent drifts, the stronger the net collapse force exerted upon it. The final operator is recombination, or G. As long as field dispersion exists, G injects heavy-tailed variation directly into the agents. The scale of this variation is inextricably tied to the median absolute deviation of the entire field. But here is the structural paradox. Despite balancing these precise forces, an n=2 system mathematically acts as a single cluster. The collapse operator dominates, the agents snap together, and dispersion drops to zero. Balanced operator mechanics cannot sustain descent on their own. Persistent metastability fundamentally requires a specific, dynamically responsive topological architecture. Scaling the agent count up to n=100 under a single global attractor still results in inevitable consensus collapse. You can introduce static multi-well stability, giving the particles pre-drawn mathematical attractors to fall into. But as this simulation shows, the particles become trapped. They stop moving. This fails the continuous activity requirement of active metastability. Theorem 4 outlines the strict necessity of axiom A4. Attractors must be endogenous and dynamically responsive, derived directly from the active field itself. Watch the Voronoi cell boundaries in this non-hierarchical swarm architecture. The k-means cluster centers are constantly recalculated based on live agent positions. The attractors track the field, rather than the field strictly obeying the attractors. Lemma 1 proves the consequence of this architecture. Because the attractors derive from the current field partition, the system is non-Markovian in its field projection. Voronoi boundaries create explicit path dependence. Two identical spatial states can yield entirely different future trajectories depending on the historic partition they inherited. The current state does not contain enough information to predict the next move. True active metastability is only possible when the attractor landscape is causally entangled with the particles it organizes, locking the operators into a perpetual feedback loop. Identifying the mechanics leads directly to the analytical question: where exactly in the infinite parameter space does this metastable regime mathematically exist? This 2D parameter map plots the chi versus tau axes, defined by the operator balance function. This function isolates the tension between recursion, local collapse, and global collapse. The lines appearing at the exact x-axis positions of 0.0891 and 0.1714 mark the boundaries of the AM window. Between the persistence threshold and the hard boundary, the minority attractor survives. To the left is regime 1, the recursion dominant zone. To the right, beyond the hard boundary, lies regime 4. Here, the operator balance function yields no solution for the attractor, and the minority collapses. Overlaying the bifurcation diagram reveals an eigenvalue decay curve that drops sharply at exactly 0.24. This is the annihilation threshold. A transcritical bifurcation occurs, the minority equilibrium loses stability entirely, and the structure slides to zero. Active metastability is a rigorously defined geometric reality, bounded by exact equations. Up to this point, the mathematical framework has treated noise as an external passenger, a fixed environmental forcing applied to the field. Axiom A6 abandons external noise entirely. It closes the final autopoietic loop by forcing the system to generate its own uncertainty. These two opposing waveform functions represent the recursion and collapse operators. Their harmonic product produces field tension. This tension mathematically spikes only when both forces pull in opposite directions. Theorem 5 proves that the system translates this structural conflict directly into a bounded noise amplitude. As the tension feeds into the generator, it produces a distinct, state-dependent noise distribution. Because this noise is driven by the state of the system, it possesses temporal autocorrelation. It creates volatility clustering, periods of sustained high variance that a fixed external noise cannot replicate. By internalizing its noise metabolism, the system sustains minority dispersion in regimes where previous models forced a collapse, expanding the accessible phase space. In its ultimate form, the framework generates the exact specific uncertainty required to perpetually sustain its own structural complexity. A valid new framework must recover established physics as limiting cases. Theorem 6 details the reduction to classical dynamics. Watch the RCR master equation. If we limit the cluster count to 1 and set the recombination operator to 0, we systematically degrade the mathematics. The remaining variables form the exact Hegselmann-Krauss bounded confidence consensus model. Reset the equation. If we apply a different constraint, setting the cluster count to 1 and introducing Gaussian noise to the gradient flow, the framework reduces directly into a standard Langevin stochastic differential equation. Classical convergence models are not mathematically incorrect. They are the degenerate, non-active limits of a broader structural reality. We can apply this mathematics directly to open-ended systems that defy equilibrium. It maps the mechanics of stubborn political polarization and outlines the precise rules of endless ecological competition. Moving beyond the binary assumptions of convergence provides the rigorous mathematical vocabulary required to understand why pluralism, dissent, and variation eternally persist.